625 plus 0.162 times sine of 60. So this is going to be positive 0.2753, and this is going to be 0.162 times cosine of 60 is going to be negative 0.081. And then your total force would be the square root of the 0.2753 squared plus the negative 0.081 squared. And so square root of that squared plus that squared gives me now a force of 0.287 rounded off newtons. And the angle, reference angle, arctangent of the negative 0.081 over the 0.2753 of that divided by that. Which gives us now an angle of negative 16.4 degrees. So yeah, if I want to be real, mean about it, I can give you all sorts of these to give you, 5 or 6 charges acting on another charge, and have you add all those vectors together. We did a bunch of that in the first semester, or hopefully you did. So no, I'm not going to make you do that for this second semester. So if I'm going to give you things where there's multiple forces acting on one charge, due to however many other charges you've got, they will be where they're parallel to each other. So you're either going to be adding the forces or subtracting them depending on which direction they're going. Unless I got enough stuff I want to grade down, I won't have to grade all that again. Okay. So that's the force equation. Well, if you got a charge, we've got this, like, it's the first 2 charges here. When we put charge 2 here, before charge 1 put a force on charge 2 going to the right, this amount. But even if charge 2 is not there, so if I've got charge 1 here, at that distance away from it, it's effectively like charge 1 distorts the space around itself. Which then, when you put that other charge in that area, or that volume, I guess, in that area, that distortion of the space around the first charge creates the force on the second charge. And that almost gets into, with gravity, Einstein's idea that masses warp space, technically warp space-time. And you'll see like Newton really didn't understand gravity. He didn't really like it, but he had to accept what it was. There was no obvious physical connection between one mass and another mass, between the Earth and the Moon. Nothing holding them together there. And so he called it an action at a distance force. But why? Why is there no obvious connection, but we still have this force between these masses? And again, Newton didn't understand that. Well, Einstein comes along after his 1915 paper on general relativity. What it basically said was that a mass distorts or warps the space around it, and therefore that distortion of the space is what creates the gravitational force on another mass. You'll see examples of, like if you take a piece of rubber and you stretch it out over a frame. and then you put a bowling ball right in the center of it. Well, yeah, the Earth's gravity pulls down on the bowling ball and it distorts this piece of rubber. It'd be like here's the piece of rubber, looking at it two-dimensionally, and here's your bowling ball in the middle of it. Well, in a very simple sense, that's like, say, the Earth does with all of this space around it, but three-dimensionally around it. And then if I put, say, a golf ball right here, what's it going to do? Well, it's going to roll down toward that, which is then effectively like the gravitational effect that the Earth has on, say, the satellite going around it. And if you give that golf ball enough speed, here's the thing, here's your sheet around it, here's the golf ball, but if you give it a speed sideways, then it will start circling. If it's a high enough speed, it'll orbit it. So that's just almost like a two-dimensional example of what's happening three-dimensionally with a mass. Well, the same thing's happening with charges. They distort the space around them. And so if instead of, in order to measure that distortion, you got this charge here, if you put a very, very small charge right there, much, much less than the charge you're trying to measure, its distortion that's going on around it. You want it real small because then it's not going to have much of an effect itself on that space. So you've got your test charge there. And what you do is you then measure the force of that test charge at different locations around this one charge that you're looking at. And if then you divide that force by that test charge, divide it out essentially, then you get that distortion, which is then called the electric field due to this charge. So this charge creates this electric field, and then if you put another charge in that electric field, you get a force acting on this charge. Looks like your F is the Q times the electric field strength. So that's that idea anyway, where that's coming from. Well, how much is this electric field? Well, if you could just think of it as force per unit charge, but the force is this K Q1 Q2 over R squared. So the electric field would be K times Q, whatever the Q is, that's creating the electric field, divided by the distance away from that Q squared. So we end up with this equation for electric field. Now, technically, this is the equation for the electric field if it's a point charge. Just a single charge, and basically the charge has no dimensions. It would also be the same as if you had like a spherical charge, a spherical distribution of charge, a perfect sphere, and the charge is evenly distributed throughout the sphere. And you're out a distance r that's bigger than the radius of the sphere itself. You'd still have the same electric field equation. But if you have any other sort of distribution of charge, then you can't use that. You got to get into something else. Technically, it would be a K times an integral of dq over r squared. And that could end up being really bad integration, depending on what the distribution of charge is. So now we don't want to really have to do that if we can get away from it. And there's ways we can do that, or either that or we just ignore those really hard problems and stick with the easy ones. But for a point charge, it's just KQ over R squared. Again, R is the distance away from the charge. Like in this one, force, R is the distance between the two charges. Don't think of that as a radius. You know it's R. It's not a radius. It's a distance from one charge to the other charge. Or it's the distance. The point is that you're calculating the electric field for away from a charge. This electric field, in general, you're calculating that at a point in space. You're not calculating it at the location of a charge. You're calculating it at some point in space away from whatever charges you've got. Again, we could have more than one charge involved. Okay, so if we've got our two charges here, 3 and 5. They're separated by a distance of 1 meter. What would be the electric field halfway in between the two? And the distance from here to here would be 0.5 meters, and from here to here would be 0.5 meters, halfway between. What's the electric field due to the 5 microcoulomb charge? I'll just call it Q1, E1. Well, it's the K, so 9 10 to the 9 times that charge, 5 10 to the negative 6, divided by the distance away from that squared. So divided by 0.5 squared. And so you have 9 times 5 is 45, and then times 4 would be 160, 170, 180 times 10 to the third, or 1.8 times 10 to the 5th. And for right now, anyway, our general units is going to be newtons per coulomb. I think force over charge is E. So force in newtons, charge in coulombs. There's also other units. You may see a problem where it says the electric field is so many volts per meter. We haven't talked about volts yet, so we won't get into that yet. But it's equivalent to a newton per coulomb and a volt per meter. They're the same type of charge. They're equivalent to each other. What's the electric field due to the 3 microcoulomb? So 9 10 to the 9, 3 10 to the negative 6, divided by the 0.5 squared. So 27 times 4 would be 80, 90, 108. So 108 times 10 to the third, or 1.08 times 10 to the 5th newtons per coulomb. But force is a vector, and E is F over Q. Q is a scalar. So E must also be a vector. So what direction is the electric field vector going to be? Well, when we do that test charge, I'm going to put the little tiny Q dot there. The test charge, by definition, is always positive. So if this was a positive charge, if this is positive, which way would the force be acting on this positive test charge? It would be repulsive, so that would be that way, and therefore the electric field must be going away from a positive charge. If the Q that you're doing the electric field for is negative, this is a negative charge, and out here some distance R, you've got your positive test charge, then it would be an attractive force that way, and therefore the electric field at some point in space is going toward a negative charge. So basically, electric fields always point away from positive charge, they point toward negative charges. And that's because of the way we're defining that test charge. Which way would the force on a positive test charge be in that electric field? So away from a positive toward a negative. Same direction as the electric field directions. So for these two, well, both of those are positive. So at that point, which way is the electric field due to Q1? Now it's away from this positive. So this E1 would be going to the right. How about the electric field due to the Q2? Well, that's positive, so it would be going away from that one. So your E2 would be pointing to the left. So this is going to the right. This was going to the left, which means, again, they're in opposite directions, and therefore you would subtract them. The difference in the two, opposite directions, so the sum of the electric field at that point would be the 1.8 into the fifth, all that positive direction, and minus the 1.08 times 10 to the fifth in the negative x direction, and so you have what's that, 7.2 times 10 to the fifth, or 7.2 times 10 to the fourth newtons per coulomb going to the right. Or again, if you just want to say that's the positive direction, it would be a plus 7.2 10 to the fourth. Whereas if, you know, you had the positive 5 microcoulombs, and then over here you had a negative 3 microcoulombs, halfway in between, then the positive would be going to the right, because it's going away from the positive charge, but the E to the negative charge here would be pointing to the right also. Now they're both going in the same direction, and so you just add the two magnitudes together. Again, for that electric field equation, think of the charge as absolute value. Put it in as a positive number, even if it's negative. Get the magnitude, then look to see what direction the vector is, either away from the positive or toward the negative. And if you've got more than one, you've got to add them together. Well, we go back to both of these being positive. Halfway in between, you've got a net going to the right a little bit. But they're in opposite directions, which means that at some point in here, they should be in opposite directions but equal to each other. And therefore, the net electric field should be 0 at some point. So where would that location be? Let me redraw some of this to make it easier to see, hopefully. So if I've got my positive 5 microcoulombs, and over here I've got my positive 3 microcoulombs. This distance is my 1 meter, and let's put that's x equals 0, this is x equals 1, located on the x-axis. So where on the x-axis would you have a net electric field equal to 0? It's just going to be somewhere here, and we're going to call that position x. And if that's going to equal 0, then the electric field due to this positive 5 would be pointing to the right, due to the positive 3 would be going to the left. And so vectorially, the E5 plus the E3 is going to equal 0. Or the magnitude of E5 is going to equal the magnitude of E3. What's the magnitude? Well, that's the K, then times the 5, 10 negative 6, divided by x, that distance squared. And the magnitude of this one through this charge is going to be the K times the 3 10 to the negative 6. And so what's that distance going to be? this distance is x, how far is it from here to here? What was the distance from here to here? And this was x, so this distance has to be 1 minus x. 1 minus x squared for that r value. Well, this is nice because I can cancel the k's. I don't have to worry about the 9, 10, and 9. I can cancel the micro parts, the 10, negative 6. And then I can cross multiply, and so I have 5 times 1 minus x squared is equal to 3x squared. So this is 5 times 1 minus 2x plus x squared plus 3x squared, or 5 minus 10x plus 5x squared is equal to 3x squared. And so I've got 2x squared minus 10x plus 5 equals 0. Got a little quadratic equation again. And so I've got a is 2, and b is negative 10, and c is 5. And that gives me x is either 4.436 meters or x is 0.5635 meters, which would be the correct answer. All right. Okay. Yeah. Why not the other one? By definition, it's somewhere in between the two, right? Which is less than a meter. That's, this one is bigger than a meter. And actually, the way mathematically, the way we worked it, that does have significance. That's from here. That's along the x-axis, so that's out here, somewhere at 4 meters, 4.4 meters approximately. At that location, these two electric fields would equal each other. But do they add up to 0? Well, the electric field here, due to the positive 5 microcoulomb, would be pointing to the right. Due to the positive 3 microcoulomb over here would be pointing also to the right. So yes, they do equal, but they're not going to cancel each other because they're not in opposite directions. So, things like that, you can end up with two answers where, yes, those electric fields do equal the same amount. And which one are you going to take? Well, it was a little simple here because we wanted something in between 0 and 1. So it had to be less than 1, which would be this answer. But then you can also think in terms of, well, okay, at the other answer location, yes, they do equal, but they're not going to cancel because they're both in the same direction there. You'd be adding them as opposed to subtracting them. So, be aware of that sort of possibility going on. So there's an electric field. We've got the electric field vectors is a vector quantity. Got that equation for electric field. We've got the force equation. You're looking at the force that one charge is putting on another charge. All of these, the kinds of problems you're going to have here, all of them are going to be dealing with point charges. Nothing where it's out of that. Okay, so there. You got that. Well, if you're thinking in terms of these electric fields, what if you had a circle? And what if I put two charges on this circle? Let's say they're on beads that can slide around the ring, and there's no friction. Plus there's no gravity, so we're looking like down on frictionless table and they're on this, connected to this ring, but they can move around the ring. If they're both, if they're both positive, where are they going to end up? Basically, across from each other, right? So if we put like one here, positive Q, and the other one would be directly across from it, positive Q. If they're both the same charge, they're directly across from each other, then halfway in between, you're right at the center of the circle at that point, right? So distance r, the radius of the circle away from that point. What's going to be the electric field at that point? Well, it's the same Q, it's the same R. Are they in opposite directions at that point? Electric field due to this one is pointing this way, and due to that one is pointing that way. So they would add up together and get zero electric field at the center of the circle. What if you add two more charges to it? Then they would end up like that. And now you got electric field due to the bottom one pointing up, to the top one pointing down. Again, electric field equals zero at the center. Now, if you add them in groups of two, they're going to be evenly spaced around the ring. Because other directions, that force between them is going to try to get them as far away from each other as possible, and so they end up, being equally spaced around this. And just, if you're adding them in groups of two. And so you always end up electric field equals zero right at the center. Nice thing about it is, even if it was an odd number, so if I had three charges, and right at the center, again, that distance is r for each one of them, and they're all the same Q. In fact, in this case, it doesn't matter whether they're both all positive or all negative. The Q is the same, the R is the same, the magnitude is the same in the electric field. But if we think of these as being positives, this one, the electric field would be pointing down. This one's electric field would be pointing that direction. This one's electric field will be pointing this direction. And if you go through the calculations, of adding vectors together now, you got your x and your y. This component and this component would equal each other and be in the opposite directions. So those two x components would cancel. And this y component up and this y component down and this y downward, or two up and one down there, would end up, again, adding up to zero. And so the electric field at the center would still be zero. Someone had asked, I was doing this example in a class one time, and someone said, well, what if it's an odd number? I said, well, it's still going to add up to zero. Okay, but, well, maybe I better, can I show that mathematically? So I did it with the three of them. And that's fine, because then, like, these angles are 30 degrees. Nice angles there. Here around here would be 120 degrees. Around the 360 degree circle. Did it with that. They all the components add up to zero. Did it with 5. Because then what 360 divided by 5 is, whatever it is, 72 degrees. And I started doing it with 7. But now I'm getting into really bad decimals. In fractions of degrees. And I says, that's okay. It will work. I knew it worked. I just didn't want to go through all the math to try to show that it worked mathematically. Plus, if you really want to do it, show that it works for no matter what the number would be, then you have to get into number theory to show that, yeah, all the evens work. That's simple because now you've always got something directly across from the other one, and they're going to cancel, the two of them cancel, and therefore all the two groups of two cancel. But the odd numbers, you know, one could have just one. 3 work, 5 work, and then you got to do 7 and 9 and 11 and 13 and 17 and dot, dot, dot forever. And I'm not a number theorist, so definitely didn't want to try to prove that mathematically. But it does work. That's two-dimensionally, okay? But it turns out also it works if it's three-dimensionally. So let's say we've got a sphere going around here. There's the center. And if you've got these positive charges, and I can't put them in here because it's hard to tell that they're on the outside. If they're all on the outside surface, and this is a conducting material, so it's like a piece of metal, it will turn out that those charges will redistribute themselves so that they are all equally spaced around this outer surface of the sphere. They just will now technically